This is the video for section 10.1, curves defined by parametric equations. So here's the big idea for this section, and in fact for this entire chapter, is the following. So if you have a particle moving in the xy plane, then the position of that particle x comma y is a function of time. And what that means is it means that the x-coordinate of your point is given by some function f of t, and your y-coordinate is given by some function g of t. And maybe you've got a specific range of t values or you don't. So these are what are called parametric equations. And the parametric comes from the word parameter, which in this case t is what's called the parameter. And we talk about parametrizing curves by parametric equations. One of the most fundamental examples of this is the following. So if we look at the x equals cosine t, y equals sine t in the range 0 less than or equal to t less than or equal to 2 pi, then the first way to get an idea of what sort of curve this is describing, and it describes a curve because, right, as t moves through this range of values, cosine and sine are both continuous, and so those x values are going to trace out continuously, the y values will trace out continuously, and so they describe a nice continuous path in the plane. So the way we get an idea of what this curve looks like is by plotting some points, and the way that we do that is with, say, a column of t values, the corresponding x values, and the corresponding y values. So for instance, when t equals 0, x is going to be cosine of 0, which is 1, and y is going to be sine of 0, which is 0. So we have the point 1 comma 0 on our graph. When t equals something like pi over 4, cosine of that is root 2 over 2, sine of that is root 2 over 2. Plug in pi, and we get the point 0 comma 1, and so on. And what we see when we plot those points, hopefully those values are familiar. There's 1 comma 0, here's 0 comma 1, root 2 over 2, root 2 over 2 is somewhere over here, and what we see is that this traces out the unit circle. And when we do this sort of a graph, what we generally do is we mark out what the t values are for some particular points, and then back around if we were to plot some more points. For instance, when we get to the end, that should of course be pi over 2 there. When we end up with 2 pi, we get back to the point where we started. And because we understand the patterns that happen with sine and cosine functions, because we've played with them so much, we recognize that this traces out the unit circle exactly once. And we indicate the way that the curve is traced out by putting arrows on the curve in periodic places. So the direction of the arrow on the graph is indicating the path along the curve as t is increasing. And one thing that you can note is we know that this is a unit circle because the Pythagorean relation cosine squared t plus sine squared t equals 1, that is when we plug in the x value and the y values that we have from our equation, that translates to x squared plus y squared equals 1, which we know from the previous video is exactly the equation for a circle. Okay. This technique of taking your parametric equations that you started with here and transforming them into an xy equation is called eliminating the parameter. And the name makes sense because if t is the parameter, then in this process what we've done is we've eliminated t from our consideration, which you can see from this new equation has no t's in it. We've eliminated the t's from our consideration here. Let's see another example of this. So this next example is going to look very similar to the previous one. So we'll have x equals 1/2 cosine theta and y equals 2 sine theta. And I'm going to consider the range of values 0 less than or equal to theta less than or equal to pi. And notice I'm using the Greek letter theta here instead of the regular letter t. This is just parameters come in all different letters. From the previous example we saw that the t value, even though we think of it as measuring time, was really indicating the angle that we're using on the circle, and so oftentimes we'll see thetas when we have sines and cosines to indicate that we're supposed to be thinking about an angle. What we're going to do with this example is we're going to eliminate the parameter like we did on the previous one in order to identify the curve. And then we're going to sketch the curve. So what we note is that the equations that we've been given are very similar to the previous ones, and the way that we were able to eliminate the parameter in the previous example was by using the Pythagorean relation. And so what I'll do is I'll take this first equation and transform it into just cosine theta equal to something. So I multiply both sides by 2. And then similarly with the second equation, I'll multiply by 1/2. And so my Pythagorean relation, cosine theta squared plus sine theta squared equals 1, translates to 2x squared. And notice what I'm doing is I'm taking the cosine that I see here. It's equal to 2x, so I can substitute it into the equation. I add to that the thing that I get substituting 1/2 y in for sine theta, and that is equal to 1 because of my equation. So this simplifies to 4x squared plus 1/4 y squared. That's a 4 down there. Equals 1. And from our previous video, again, ideally we recognize this as the graph of an ellipse. And it's a nice ellipse centered at the origin. There's no completing the square to be done here. The only thing we need to do is manipulate the equation a little bit in order to put it into the form that we're used to thinking about. So I write this equation as x squared over 1/4 plus y squared over 4 equals 1. And then to make our box easy to read, it's x squared over 1/2 squared plus y squared over 2 squared equals 1. So in the language that we used in the previous section, we have that a equals 1/2. That'll be the x width of our box, and b equals 2, which will be the y height of our box. So our sketch here and here, and if this is 1, then for my x width I need to use 1/2, and then my height, try to draw this to scale, will be 2. There's 1 and there's 1/2. So my box for my ellipse fits into this shape. And my ellipse, I'm not going to draw it in solid, I'm going to draw it in dashed, and I'll explain why in just a second. Now the reason that I'm drawing the ellipse in dashed is because what we haven't used yet are the limits for the theta values that we're considering. And so the last thing that you want to do is plot a couple of points using the theta values that we've been given in order to make sure to see which piece of the ellipse we actually use for these values. So I'll make a table of values here. So when I plug in theta equals 0, my x is going to be 1/2 cosine theta, so that'll be 1/2. My y will be 2 sine theta, which is 0, and that tells me that my starting point is right here at 1/2, 0. Now when theta equals, say, pi over 2, then I'm going to get cosine of pi over 2 is 0, and 2 times sine of pi over 2 is going to be 2. So I will have this upper point, my ellipse, next. And notice that as I sweep out the values from 0 to pi over 2, I will exactly sweep out the angles from 0 to pi over 2 corresponding to these points on the ellipse. So we get the first quadrant piece of the ellipse, and then for the later values, say from pi over 2 to pi, we go to negative 1/2, 0, again just by plugging into our equations, and that sweeps out the next quadrant of the ellipse. And it ends right here. So again, we put in some arrows in order to indicate the direction of the curve as t increases. Okay? Sometimes you'll sweep out half the curve, sometimes you'll sweep out the entire curve, sometimes you'll sweep out the entire curve 2 or 3 times, and so one has to do this final point plotting bit in order to see which pieces are being swept out. I want to very briefly talk about one more important example from the text on the next page, and then we'll be done. So the next example, and I'm not going to derive this, you can look in the the book at example 7 for this is the cycloid. And the way the cycloid is described is geometrically. I'm going to look at the coordinate axes x and y, and I'm going to start with a circle of radius r and a point on the circle here. And what's going to happen is that this circle is going to roll in a is going to roll to the right and sweep out a curve in the plane. So for example, if it rolls a little bit over here, maybe that reference point that we started with has moved all the way to the top, and so I've swept out a curve that looks something like this. And it continues to move through the plane to give a curve that looks like this. And so on. Now the point of this example is that you can actually write out x and y, a single equation that describes this, but it's really gross and complicated and hard to do calculus with. And so what we're going to see, if you read through the example in the book, that the parametric equations for this are actually reasonably straightforward. These right here. And when we get into the sections where we start doing calculus with parametric equations, we'll see that, for instance, to compute the arc length or to compute the area under this curve, that these parametric equations make life very easy, whereas the xy equation would make life really, really complicated. Okay. So this is the end of the lecture on section 10.1 on parametric curves.